Thank you. I'm just realizing that this little laser pointer is not going to show up on this screen if I have my speaker notes. It's going to be very inconvenient. What was that, Earl? It's not recorded.
Oh, I think it'll record that.
No, it should record the mouse pointer. Yeah. All right. Hello, everyone. I'm Craig Gidney, and I'm going to talk about giving a threshold to the Bacon-Shor code by deleting operations out of its circuit. This is work that I did with Dave Bacon, who you may know as the Bacon in Bacon-Shor code. We worked pretty closely coming up with the underlying ideas of the paper. Other than that, I contributed most of the coding and the writing, and Dave contributed most of the jokes. Now, you might think that contributing most of the jokes is not important, but I actually have some solid evidence that it is. In 2004, there was this book published called The Wisdom of Crowds, where it's argued that aggregating the opinions of many people is more reliable than any one of them. The modern version of this is a kind of aggregation that we call internet points. So the most objective way to rank the importance of papers is using internet points, and we have a website for doing this called SciRate, which is a social site for assigning internet points to scientific papers. If you look at all the papers on SciRate that have me or Dave as authors, sorted by internet points, you get this. Down here in the runner-up area, you have multi-year milestones from the Google quantum computing team. These are each the culmination of tens of thousands, maybe even hundreds of thousands of person-hours of work. Engineers and scientists grinding away at this field-defining problem of building a fault-tolerant quantum computer. But at the top, with the most internet points, you have less bacon, more threshold. A clear example of the importance of a solid joke. Okay, now I've established the objective importance of the work. Here's how the talk is going to go. First, I'm going to tell you what a Bacon-Shor code is, because probably not everyone here knows that. Second, I'm going to talk about the changes we made to improve the Bacon-Shor code. Third, I'm going to convince you that those changes actually fix what they were supposed to fix. And then I'll sort of talk about what it all means. So what is the Bacon-Shor code? The Bacon-Shor code is a topological code built out of two-body operators. It's roughly 18 years old, and the main strength of it is actually the simplicity of these two-body operators. They're pretty simple to implement in hardware. You have a grid of qubits, and all you're doing is measuring two-qubit parities between adjacent qubits on the grid. For qubits that are horizontally adjacent, you're measuring x parities. For qubits that are vertically adjacent, you're measuring z parities. And that's it. It's a very simple circuit to run. In modern terminology, this is called a gauge code because lots of these measurements anti-commute with each other. So it's not like a stabilizer code where you can just compare each measurement to the measurement from the previous round in order to check if things are going wrong. You have to consider combinations of the measurements. Specifically, if you multiply all the measurements along a column, like here, and I really apologize if I can't do the laser pointer well from this perspective, then you get a stabilizer, such as this stabilizer here. And that stabilizer commutes with all the measurements you're doing. And so you can compute that product of measurements every round and compare that in order to get detection events. And similarly, along the rows, you can multiply all the z measurements in order to get z stabilizers that survive. Here's an example of a Bacon-Shor circuit schedule. Each qubit needs to be involved in 4 parity measurements, or up to 4 parity measurements. And this is a 4-layer schedule that does all of those measurements. I should mention that in this paper, we assume that 2-qubit parity measurement is just a native gate that you have available. For hardware where this isn't a native operation, you'd have to decompose it into a series of other operations that you do have. But for the purposes here, where we're mostly interested in the threshold, that won't really matter since that can't change whether you have a threshold. In this schedule, you do the x measurements first. That's these 2 layers. And then you do the z measurements. That's these 2 layers. And we measure half the x, and then the other half of the x, half the z, then the other half of the z. Although this is the ordering that we use in the paper, it's not the only ordering that's possible. In particular, you might think that you can't swap the order of these 2 layers here because they have measurements that anti-commute with each other, but it's actually fine if you do. You get a slightly different fault-tolerant structure, but it's still fault-tolerant. The Bacon-Shor code has one enormous problem, shown by this plot. The x-axis here is how big of a Bacon-Shor code you're using, so what's the diameter of the grid. The y-axis is the achieved logical error rate. The curve is showing what logical error rate you get at each size for a circuit noise model where each gate has a fault rate of 0.1%. To help you interpret these results, I've added this dinosaur. On the left, the dinosaur is happy because things are improving, and on the right, the dinosaur is sad because things are getting worse. The reason things are initially getting better is because the code distance is increasing. A logical error in the Bacon-Shor code is a set of physical errors crossing the entire grid. So if you have a grid of diameter 50, you need 50 physical errors to make it fail. As you make the grid bigger, you need more physical errors to cause a logical error. The reason things stop getting better is because as you make the grid bigger, you're multiplying together more measurements to get each check. And this is making the checks noisier and noisier and noisier, and eventually that gets so bad that it actually overwhelms all the gains in code distance that you're getting, and then some. This behavior isn't specific to this noise strength. This is generic. No matter how small you make the gate error rate, you'll see this pattern of initially it gets better, and then it hits a minimum and it starts getting worse. In the lingo, the Bacon-Shor code lacks a threshold. There's a limit to how good you can make it. There's a reasonably long history of people fixing the Bacon-Shor code's threshold. And to be honest, I'm not too familiar with the details. I kind of wish Dave was here to talk about it. He could give a very good summary, but he's unfortunately on the other side of the planet. But here are two examples. There's a 2007 paper by Lattice et al. That concatenates the Bacon-Shor code with itself. At the time, my understanding is that this actually gave the best provable threshold of any known code. By the way, we're also going to concatenate the Bacon-Shor code to get a threshold, but we're going to use a different technique to do it. This paper is concatenating it using sort of code-agnostic techniques, like the Shor method or the Stein method, that aren't specialized to the Bacon-Shor code. And the major downside of those techniques is they completely break the physical connectivity. Like, they have no idea you're trying to map things onto a grid, and they won't preserve that fact. This second paper is another example of trying to give it a threshold, where they do more work to preserve the connectivity using a different technique where they mix in patches of surface code amongst the grid. This breaks up these really long stabilizers into shorter runs. That also works, and it's definitely much more respectful of the physical topology of your device. But it is still sort of demanding something more from the hardware, like more capabilities in the little patches where you can do the surface code. It's very likely if you had hardware where you could do this, you might just want to do the surface code only. Okay, that finishes my very inadequate summary of the historical context behind this work. Let's talk about what Dave and I actually did. But first, just a tiny little bit of history about lattice surgery. Lattice surgery is a well-known strategy for performing fault-tolerant operations in the surface code. The way lattice surgery works is that you take two adjacent qubits, you temporarily merge them into a larger qubit, and you're rewarded with a fault-tolerant parity measurement. As you've seen mentioned in other talks, lattice surgery also works in codes besides the surface code. In particular, it works in the Bacon-Shor code. That's what this slide is showing. If you take two Bacon-Shor logical qubits, turn on the physical parity measurements between them to merge them into one big logical qubit, then split them back apart, that's a fault-tolerant parity measurement. Here in the top right, you can see where the measurement result is coming from. These two columns are the two logical X observables from the two logical qubits before they're merged. And these little red wedges are the physical measurements we're doing. And if you multiply all those little wedges together, you get the two columns on either side. So a product of what we are measuring is what we want to measure, and that's why this is a parity measurement. In order to really show it works, you also have to show that the individual logical X observables survive the process, and in particular, the Z times Z observable survives the process. The individual Z observables won't survive this because the individual Z observables run along the top here. And when you merge it together, that observable would be, for example, along these 5 qubits, and it anti-commutes with this measurement. But when you combine them together, two anti-commutations makes a commutation, and that's sort of a core part of why this works. To really convince you that it works, here's the result of benchmarking Monte Carlo samples of that circuit of Bacon-Shor lattice surgery. So this is based on logical qubits that have a grid diameter of 5, and it's holding the lattice surgery for, I think, 5 rounds. The x-axis in this case is the gate error rate, so this is the noise strength. And the y-axis is the logical error rate for the entire lattice surgery measurement, and this is including everything. This is including that the 2 x observables must survive, the ZZ observable must survive, and the measurement result must be correct. So this is end-to-end, did it work? You can compute the slope of this line in order to get the suppression, and it's quadratic suppression in this case. And that means that the effective code distance of this construction is 3. The reason it's 3 instead of 5 is because in our error model, 2 qubit parity measurements, when they fail, can destroy both qubits that they touch, and this cuts the code distance in half. There are ways potentially to avoid that, but again, we were mostly interested in showing that there is a threshold, and so we don't have to fix that. So we have lattice surgery parity measurement in our toolbox, and the Bacon-Shor code can be implemented entirely with parity measurements. So a natural thing to do is to combine these 2 things, implement a Bacon-Shor code at the logical level by using lattice surgery to do the parity measurements required by the code. Here on the left, I have a diagram of 25 Bacon-Shor qubits forming a 5 by 5 grid of logical qubits, which we're going to use to run a Bacon-Shor code. Each of these logical qubits is itself made up of 5 by 5 grids of physical qubits running a Bacon-Shor code. On the right, I have a diagram showing what the grid looks like during one of the 4 layers of parity measurements we have to do. This is the MXX evens layer from an earlier slide. But now it's being performed using lattice surgery instead of with native gates. So we can use lattice surgery to concatenate the Bacon-Shor code. And importantly, we're only using local connections in order to do it. This grid has no shapes that go across it in any complicated way. Something interesting about this way of concatenating the Bacon-Shor code is that the operations we're using are a subset of a larger Bacon-Shor code. So on the left here, I have a Bacon-Shor code on a 25 by 25 grid. And on the middle and on the right, I have those diagrams from the last slide. And what I want you to notice is that every shape that appears in the middle or on the right also appears on the left. Like the way you get from the left to the right is by deleting things. For example, deleting the blue shapes along this row. This gives a new perspective on the construction. So instead of thinking additively, where we're building up layers of concatenation, we can think subtractively. And that's great because having different perspectives like this can lead to different ideas. For example, if you're thinking in terms of concatenation, a natural idea is to change which code you're concatenating. Whereas if you're thinking subtractively, a more natural idea is to adjust the cuts you're making. For example, we hold lattice surgery for multiple rounds, which is sort of like making deep cuts. And what if we made shallow cuts instead? Actually, as I'll return to later, shallow cuts do seem to work better. This diagram is really describing the construction as an edge subtraction sort of construction. So in this diagram, we're concatenating at distance 5. So you see a different row or column every 5 steps through space. And additionally, at powers of 5, you see difference. So every 25 steps, there's an especially different column or row. And the same would be true at 125 and 625, though this is not large enough to show that. The syntax here, the labels above and to the left, are rules for when the edges are included. What you do is you're always at a given circuit layer T, and if T is congruent to X mod Y, where X and Y are from the label, then you include the edge in that row or in that column. You can sort of see that the rows and columns are turning or forming a simple sort of fractal, where if you were to zoom out, you'd see the same pattern on bigger and bigger scales. So we call this the fractal Bacon-Shor code. Now, before I can show you the next slide, I need to quickly review some concepts that Matt McEwen and actually several other speakers covered in their talks. because I'm going to show you a type of diagram I call a detector slice diagram, and you don't actually know what a detector slice is, which will make it very hard to understand the diagram. This is a circuit diagram showing repetition code circuit, or a part of a repetition code circuit. There are two measurements in the diagram. They always agree with each other, so we say they form a detector. If we ever see this pair of measurements disagree, we know that there's been an error nearby, and this blue highlight is showing us where the error might be. And we call this the detecting region of the detector. Something useful you can do with the detecting region is take a time slice of it. And when you take a time slice of it, you get a stabilizer of the state of the circuit at that point in time. And maybe even more importantly, this is a stabilizer that you really care about. Like, it's in the basis that you want because it directly corresponds to something that you're going to check. So one way to look at the structure of codes as they execute is to take this series of slices of the states and just look at what the stabilizers are doing. And if you do that with our construction, you get this. I am very happy to see that the animation is playing. I hope it's recording well as well. So here are detector slices from our construction, from the fractal Bacon-Shor code. What it's doing is stepping through the circuit, taking slices of the detectors, and then drawing those slices as these shapes. In the X-basis stabilizers on the left, you can see checks are coming and going, merging and splitting, and generally just changing over time. In the Z-basis on the right, you can actually see the state establish itself. Like, you might see that white flicker. That's actually the circuit starting over, or the animation starting over. In the circuit, I prepared the data qubits in the X-basis, and so it didn't have any Z-basis stabilizers initially, and so they slowly come in as the levels of concatenation play out. I really like this animation, not just because it kind of looks cool, but because it really shows that you should be thinking about this code in terms of time dynamics. You don't really want to think about it statically. Every one of the pictures flashing by actually corresponds to a valid stabilizer code, and the system is in that code state at that moment in time. But interestingly, I think every one of these codes is individually kind of bad. So it's actually important that we're not just staying in any one of them and are instead kind of endlessly jumping from one to the next through code space. Something I can't really explain in detail in this talk, but I want you to be aware of is the task of finding detectors. So we were showing detector slices, but I didn't really explain to you what the structure of the detectors was. Basically, our circuit is this big soup of parity measurements. And the key to finding detectors in a soup of parity measurements is knowing how detecting regions are allowed to move through the gates. So here I'm showing some examples of X-basis detecting regions moving through parity measurements. The basic rules are that if you are trying to move through a parity measurement of the same type, anything that comes in must come out. You have to touch an even number of ports. And if you try to move something through something of the opposite basis, you have to touch none of the ports or all of the ports. And so on the right here, so on the left is examples of how you can move through, and on the right, it's kind of combining those examples into this closed shape, forming a detector. In the paper, we give a simple algorithm for our circuit for finding the detectors based on union find. Essentially, you always know that a measurement is compared to itself in the next time step, and anytime there's an anti-commuting measurement in the other basis, you just join things together, and that gives you the detectors that we use. Okay, so we deleted some edges, we made some cool animations, but how well does it actually work? And well, it works pretty well. At a 0.1% gate error rate, as we saw before, the Bacon-Shor code hits this minimum amount, this minimum around a grid diameter of 25, and then it starts getting worse. So sad dinosaur. The fractal Bacon-Shor code is better pretty quickly, and it doesn't stop improving at a grid diameter 25. It keeps improving, and it's still improving at a grid diameter 45. So happy dinosaur. Except, when I look at a plot like this, I'm still left wondering, does it really keep improving? Like, does this line actually keep going down, or is it secretly just a wider parabola? Are these ripples here, are those just sort of a benign artifact of the grid diameter going in and out of phase with the powers of the concatenation distance, or are they the first signs of trouble on the horizon? So numerical evidence isn't enough to be really sure there's a threshold. It could always be that there's a problem lurking just a little further out. So if we want to be sure, we have to prove it. To prove there's a threshold, we're going to go back to the concatenated picture, and we're going to use a technique called extended blocks. So we're going to think of the construction as being built out of a few types of blocks. In this example, I have an idle block and a merge block. In the actual construction, we have more blocks than this. We have idling, X merging, Z merging, X preparation, Z preparation, X measurement, and Z measurement, and I think I got that list right. But that would be quite a lot to draw on the slide, so we're going to do this simpler example. Anyways, the key thing is that we can take these physical blocks and use them to build logical blocks that do the same thing at a larger scale. So we have a logical idling block, and we have a logical merging block, both built out of physical idling and merging blocks. And we can keep recursing this construction to make ever larger, logicaler blocks. We model the physical blocks as having some probability of faulting. And if they fault, they can break arbitrarily and adversarially. The key property that our logical blocks need to satisfy is that they can survive one of their physical blocks faulting. So if there are two physical faults within a logical block, the logical block might fault, but if there's only one, it has to correct it. A complication here is that under the hood, the logical blocks are doing things like comparing measurements between adjacent physical blocks. And these comparisons can reach across the logical block boundaries. So there's always this sort of overlap area where a fault could affect two blocks. That's the extended in extended blocks. And we deal with that basically by just overcounting when we're analyzing a block and just pretending that the physical blocks adjacent to it are also part of it. So in this example, I've been drawing a logical block, or the biggest logical block we have is made up of around 60 blocks, accounting for the block extension that's more like 80 blocks. And from that, we can compute a bound on the threshold. So in order for the logical block to fault, at least two of these 80 physical blocks must fault. The probability of that happening is at most the physical fault probability squared times the number of blocks squared. You get an inequality from that. Our goal is for the logical fault probability to be smaller than the physical fault probability. That's what it means to have a threshold in this case. And rearranging the inequality you get, you can determine that for this example, it has to be, the threshold is at least 1e minus 4. In our actual construction, the extended block count is not 80, it's more like 700. A major contributor to that is we need to use a grid diameter of 5 instead of 3, because when one of our parity measurements fails, it can break 2 qubits instead of 1. But even though 700 is a big number, it's still a finite number, so you still get an inequality. You can still rearrange that inequality and get a threshold. If you do that, you get simple proof that our threshold has to be at least 2e minus 6. Now, it's certainly possible to do that block analysis a bit more carefully in order to get a better number. I'm sure there are many people here that could do that. But in terms of getting the best possible number, I think this whole block-based proof method is kind of going down the wrong path from the start. You shouldn't be decoding the fractal Bacon-Shor code using a block-based decoder. You should be doing it actually using matching. In order for a circuit to be matchable, it's sufficient for X errors and Z errors to each produce at most 2 detection events. If your circuit has that property, we have open source tools, STIM and pi matching, that will automatically figure out how to decode it. One way that you can tell that this code has this property is that in all the det slices that I showed, they were always like these sort of tilings that you could 2-color. So every data qubit touched at most 2 stabilizers at every moment in time. So because of that, the fractal Bacon-Shor code is matchable, and we can apply matching. The great thing about matching is that decoding using matching is sort of like switching away from the code concatenation picture back to the edge deletion perspective. The matcher's not told anything about hierarchies or building blocks out of bigger blocks or anything like that. It's just given one flat matching graph that is the entire decoding problem. And it gives you the minimum for that entire problem with no regard for the imaginary conceptual block boundaries we use to make the circuit. This naturally results in information being passed between the small scale and the large scale, where certainty or confusion kind of gets passed up and down. In a block-based decoder, that would be called soft decoding or soft information, and it's one of the most important things you can do in that sort of decoder in order to improve its performance, and here we're getting it kind of implicitly for free without even really thinking about it. So going back to our question of what does this yellow curve do? We proved that the code has a threshold, so if the gate error rate is low enough, the curve will keep going down. Except the threshold we proved was for a smaller error rate than this, and we didn't even prove it for the same type of decoder. We proved it for a block-based decoder, whereas here I'm using a matching-based decoder for the simulations. This curve happens to be using that shallow cut thing that I mentioned, where we hold the lattice surgery measurements for less rounds, which is great for matching. It makes sense, I think, in the context of matching, but completely violates the assumptions of the block-based proof. So it is still conceivable that this specific part of the specific curve could go back up. Although, on the other hand, I mean, look how low this curve is getting. It's almost getting down to 1 error per billion rounds. Like, who cares if I get arbitrarily good? If you give me a computer that's this good, I can turn it into one that works. Like, this is good enough for practical purposes. Except, even though this is, I think, good enough to be practical, or at least borderline practical, though it'd be a little expensive, there are other codes out there. In particular, there's this code by Hastings and Ha called the Honeycomb code. It uses essentially the same gate set, so parity measurements, and it requires strictly less connectivity, so a hex grid instead of a square grid, and it achieves better performance. So that doesn't technically take away from the fact that we gave this code a threshold, but it's a bit of a downer. Okay, so now you understand the Bacon-Shor code, you understand the construction, you are hopefully convinced that it does the thing it says on the tin. Let's make some closing observations and get out of here. First, I'm going to talk a little bit about potential future work, which I have no plans of doing, but maybe someone here would be interested in doing. I want to emphasize that there's probably more you could do to make this construction better. You know, we always concatenated at the same distance, and we never tried deleting more complicated patterns of edges. I'm sure if someone here put their mind to it, they could improve on our numbers. Another way you can improve on this work is to fix the fact that the threshold proof uses a totally different decoder from the actual simulations. It's pretty clear to me, at least, that if someone looked at this closely also, they could give a much better threshold proof. A little more abstractly, one way to build on this result would be to take the ideas in it and apply them in other contexts. So in particular, one of the ideas I took away from this paper is the fractal Bacon-Shor code performs pretty well despite having some pretty enormous stabilizers. If you remember from that animation, sometimes there were stabilizers going all the way across the grid. And I've always assumed that enormous stabilizers are a terrible idea. Like, you might think they're okay in a phenomenological noise model where they're just sort of a unit operation, but as soon as you start doing circuit-based things, it becomes insane. And you know, given the focus of the field on finding low-density parity check codes, I think most of us here think it's a terrible idea to have giant stabilizers. But my experience in this paper has sort of actually changed my mind on this. It's okay to have some enormous stabilizers as long as there's not too many, and as long as you're allowed to check them rarely, so you're not stalling the cycle for other checks, which have to be checked faster. In fact, I'm working on a paper with Michael Newman where we apply this idea to the surface code, and we get some results that I think are pretty exciting. Hopefully that should be published within a month. Those were the looking forward slides. This is the looking backwards slide. The construction we found is to apply lattice surgery to the Bacon-Shor code. It really isn't that complicated of an idea. It's pretty obvious, at least it's pretty obvious in hindsight. And if you look at the timeline where the Bacon-Shor code was found 18 years ago and lattice surgery was found 10 years ago, it really seems like this idea was ripe for about a decade for anyone to stumble across. I asked Dave Bacon and Michael Newman, who've worked on this problem in the past, what they thought. Like, was there some conceptual block? Like, why didn't you notice this thing? Which is sort of an unfair question. They pointed out that tooling used to be a lot worse. Concatenation had already been tried, and that lattice surgery Bacon-Shor paper that I cited, not everyone's read that. Stuff like that. In my case, I think knowing the ZX calculus was very helpful to seeing the idea or to having it be closer. So maybe the fact that the ZX isn't widespread was an obstacle. Ultimately, it's kind of hard to answer a question like this. It's sort of like asking Thomas Edison why he didn't put wheels on his luggage. What are you going to do? Okay, so summarizing the whole talk, we took the Bacon-Shor code and we fixed its lack of threshold. We did that by concatenating it using lattice surgery, or equivalently by just deleting gates out of it that were hurting it more than helping it. The result outperforms the Bacon-Shor code, and it has a threshold, and it would even look borderline practical if it wasn't completely outclassed by the honeycomb code. That said, some of the underlying ideas, like taking a circuit-focused approach to decoding, using fractals, using time dynamics, allowing a few large stabilizers, those ideas that are maybe not called out so much in the paper, but are sort of core to making it work. I think those are notable and they'll be useful far beyond it. And hopefully you'll see some of that in our upcoming work. So that's my talk. It might not be quite as exciting as some of the experimental talks that we've seen, but I had a lot of fun doing this work, and I hope you enjoyed listening. Thank you for your time. Yeah, we have a question. Oh, sorry, do you want to?
Yeah, that's fine. We're plenty of time.
Seeing as the threshold for your experimental stuff is looking like it has one at 10 to the minus 3, and it gets you orders of magnitude below your proven threshold of 10 to the minus 5 or so, would it not be possible to glue those two things together to create, even not a full mathematical proof, at least pretty good empirical certainty that this does work at a threshold of about 10 to the minus 3?
I think we already have pretty good empirical certainty. That idea of using the shown result and then concatenating from there, that sounds like a completely plausible idea to improve the proof.
Thank you.
Yeah. Like I said, we were mostly focused on getting a threshold and then publishing it, because this was sort of like a paper we were doing on the side and didn't want to spend too much time on. There's a question over there.
Hi. Thanks for the great talk. I guess I have kind of a super dumb question about the animation that you were showing us about with the detection events, was that?
Yep.
So what decides the frequency of the larger white strips that we're seeing?
Essentially, when you see a long strip across the grid, that is in the other basis, the lattice surgery turning on. And so the rate at which those white strips show up and go away is kind of showing you the cadence of the lattice surgery at the various levels of concatenation.
But is that state dependent, or is that?
Oh, you can sort of derive it from this here, where the lines that have larger numbers show vary less often. I don't think of it as state dependent because it's all planned out ahead of time what it's going to do. So it's not like it has to be adaptive. It's certainly dynamic, and in that sense, it's state dependent.
Okay. All right. Thanks.
Yeah.
So my question is, you said on this slide, in fact, that these are all lousy codes. So can you elaborate on that? Because I would think that if one of your instantaneous codes is bad, that creates a vulnerability.
That's a great question. The way that they are lousy is not that they have low code distance, for example. It's that if you gave me one of these and said, please implement that, it's got these weird long stabilizers. And if I tried to implement it in a sort of normal way, I would end up with a terrible circuit, especially if I tried to measure all the stabilizers every cycle. So it's once you go into the circuit picture that it sort of becomes a problem. And you would probably fix that problem similarly to what we've done here, where you measure some of them less frequently, in which case they become much less bad.
If I were to apply this idea straight away to the surface code, what would be any conceptual difficulties to doing so? Because it seemed like I can just do this for the surface code with a bit of extra tweaks.
Yeah. The main issue with applying the idea straight to the surface code is the surface code is not a gauge code, and so the benefits of skipping some of the operations are much less. So you don't get additional checks, you get fewer checks in the surface code. But the concept of taking the underlying kind of ideas, like modify the circuit or use a few big stabilizers, those you can apply. So I guess the main difficulty would be, being careful in which things you pick and porting over the correct ones.
So you said the ZX calculus was one of the ideas that made this possible, but I see a distinct lack of spiders on your slides.
Yes,
How
I
is
have-
this ZX influenced?
That's right. I've completely obfuscated how I found the idea. It was also the, how do I explain this? We draw these 3D topological diagrams you saw in Daniel Latinsky's talk that are isomorphic to the ZX calculus. My first inkling of doing this was like taking the Bacon-Shor code and drawing one of those diagrams for it. And then it was sort of obvious that I could scale it up and copy paste it and so forth. Yeah. I think I'm at my 45 minutes.